That would make it. That would be.
First comment. Thank you. Oh.
It's vulnerable. The same group, right? Okay.
Come on, stop this.
Just a couple of comments about first case study. Maybe I just run this. At the moment I didn't put this on my yet, and this is not meant to be complete solutions, but it be something, some points that I could base it in Dow data set. Assume that I use that node 5 to do this, and so that's the perfect, right? With all the levels kind of just do this first. And this is a Dow data set, and then this is kind of setting up. I did some kind of a running this code to node 05, and then I did space by levels, and that's here. Of course, all the levels within the data sets are automatically generated with some abbreviation, and they are very imperfect, right? But you can see that for example, a data set. So here you can see this kind of setting there. And you see kind of strange, very strange levels, but I do have this correspondent in these labels here. So anyway, it doesn't matter. We can still just do it. By the way, this is not uploaded yet, so I didn't just go through this. It's not meant to be a complete solution to the wrong thing. Suggest a solution halfway. Actually, first comment is about that education number. It's actually completely in line with education. And basically, the number, this is not numerical. It's just giving the order of this education label. As you can see, you can actually use this command. I kind of generate this. I set this education number and pin with like this is 0 to D, like you have 1 to 16, okay? And for 1 to 9 they appear with 0 begin with, so 0, 1, 0, 2 to 0, 9, and 10, 11 to 16. So these are the 16 labels for that. All from this education number. I kind of pairs this information together with education. Which is already installed, this Dow data already installed as a vector, right? I use a separator to separate them. Let me run this result. By the way, I'm going to upload this to our website. Currently, don't do this. And look at the unique labels of that. So here I create this, for E, this would be so unique of E. You can see this is pretty much in line with that. I guess, I think you will find this out. Okay? So 01 is preschool, 02 is the first and fourth grade, 03 fifth to sixth, and so on up to the sixth. So actually, when you make this vector, this vector is supposed to be constructed as an order category. In my previous handout, I actually did talk about that, but here you should do this order category, which is also true in the German credit data. Some of these input variables are actually order category data or ordinal data. So you probably need to make it as an order, okay? Rather than just the regular categorical vector, which is nominal by default. So you can see that if you look at all these unique values of that combining education number and education, you can actually see there are only 16 possibilities and reading languages for the level of education. Right? You can see here. So what I'm going to do is just suppose you can, or this is already, it's up to you. I can create this one, and then I create this EDU2 and show with the result later. So I add, this is a new variable we added to the adult data set for those who already created. Okay? And with this adult data set, we basically take vector education number. Okay? And the labels will be the labels we just created. And what you have to do here is just add one thing called order equal to. So that will create all the categorical data. If you run through this with adult levels, EDU to show levels, you can see the result. Like this. So here this is the level. So this data set. And of course you can also just to show a few of this data there. Just show the first 20 observations. So basically, this is all the categorical data, the first 10 observations as such, and you can actually see the level 01 less than 02. You see this additional information. These are all the categories. I think this is really important to have this result, and then if you were to show like mosaic plot for that. Before that, let's see if we have, look at is there any missing values in that? Or it just happened in this data set, there's no missing values of education level, so we can actually see that. To show it's all complete cases. Basically, this return a vector of length, in this case 30-some thousand, same size as the number of rows, indicating true or false whether this particular variable is missing or not. Missing is false and not missing is true. Okay. So here we say all complete cases of that. So there's no missing variable. Right? No missing variable for this data. Before I look at the second one, let's do this. Look at this mosaic plot. Okay, of this EDU2. You regenerate it, right? Without regrouping, okay, so this is the result. And now this is in right order, okay? This is according to year of the level of education, right? So there's some slight reverse here, as you can see. Maybe due to sampling error or something like that. This is not what we would expect, but not too much different. And this, in general, the general trend is that there's more education is very greater than 50K tend to be. The For this one,
Yeah. So I know the bar chart, you can like turn things sideways and stuff, but I couldn't figure out how to do it. Let's see.
so
Did anybody?
you can do rotation. But we do need some more space on that. Let's see. I think the way to do this. Let me leave some more space there. Write some more serious stuff there. So leave about 8 lines of text. How about instead of doing this vertically, let's do horizontal. See if that works. Vertical is for what direction to that. Sometimes it's confused. You might remember how we do this direction. Horizontal, vertical, vertical. Here's this thing. Written on the right hand side, left hand side, so I can only do this. Well, this work. Let me just change this back to the. Anyway, so we can do this way. Probably easier to see, right?
Yeah.
Even this was still hard because we have so many different variables. So here we do the, according to this, we do the horizontal split first, right? Horizontal split and then followed by the vertical split. I think this part will automatically leave room for that, so actually you don't need to adjust for this. So even this, you don't need to do this. Yeah, you don't need to do that. Just do it horizontally. Because there's always a way to do it vertically. I can let it rotate like 30 degrees. But we don't need to. We don't need to do that. Okay, so here this is about that. And let's look at where are we at? Oh, in fact, I said that here this is stuff. Before this, before I forgot, maybe we do this one. this additional argument LS equal 1, I think it's essential. Try without it. LS equal 1 means the label for the sigma is always horizontal. Space label. So now we have LS equal 1. You can always try this out. They're going to come together. So we need to specify that LS equal 1. I hope this is helpful. So here LS requests the label for the sigma is always horizontal. Okay, anyway. The other thing is that, well, of course, you can do regrouping, and the one I put it up, this may not make sense. Of course, when you do regrouping, you have to ask yourself, is the outcomes of the regroup making any sense of it? You want to do that, make sense of that. Or maybe this is one of many directional regroupings. Anyway, suppose I do it this way. Okay? One of the groups that just does this way. So let's take that and show the result. So if you do regrouping, one regroup education levels. Okay, so without data set, the cut command basically allows you to kind of separate into several data sets, sort of categorize your numerical data into class intervals. Here I didn't use equal with class intervals. So in this case, that education level, okay, between 0 and 8, okay, and by default, cut function uses right inclusion. So any intervals, they will include its right boundary, and also by default, the leftmost, if left is included, the leftmost interval also includes the left boundary. So except for that, 0 to 8, so 8 is inclusive in the first group, and then the next one is above 8 to 9 inclusive. So this will just break this into several class intervals. So from 0 to 8, I said this is less than high school grade. That's the case, right? Isn't it? We actually seen that the label earlier. This is the label we have seen earlier, right? Your education number up to number 8, those are less than high school. Here at high school, right? Here high school, I mean high school graduate. So here between 0 and 8, I classify that, and then from 9 to high school graduate, this is expert. And between 9 and 10, some classes, maybe you want to merge the other two as well, so some idea. But depends on how you do the regrouping, whether the regroup result is reasonable. Okay, suppose I do this way. I use the D for right inclusion. So basically done by the cut function. Okay? Cut function take a numerical data, and then with the breaking points, you kind of pin the data set into these class intervals. Okay? So here between 0 and 8, we have this 8 and 9. High school, okay, 9 and 10, and some classes. This is right inclusion by default. Okay? So according to this, this will be the labels. And you all have, for the breaking points, you always have one more numbers that the labels you have, right? You have this n plus 1 in numbers define n intervals. These are the labels you have. And the key is that at the end of this cut function, okay, except for the numerical data you have, the breaking points you have, and then the labels you have, add one more. The result will be auto-categorical. Like in this case, actually, auto-categorical makes sense. And just clean this up. I want to remove this. Okay, this E and LEV, we just use that. If you really you want to save this back to this adult data set, you can do so. So save the image of this adult data set. So this is okay. Anyway, and then of course now you can show this EDU3. Let's show the first many observations. So now here you have, probably I have a very bad choice of this. So that's in high school, so this is all the category. This is the levels names for that first level. Less than high school, very good. Less than that. So it's all the category. And look at our second mosaic plot. Probably for this we don't need to do anything with transfer. Still is there. Okay. Maybe it's just in some space. Okay. So we can use that. Okay. Change it. This is as expected, right? So you have you expect see education tree is going from top down, the level of education becomes higher and higher, and then the proportion is of say earning more than 50K. For example, how do you make of this capital K? Zero means no investment of the actually that's zero, right? There's no capital gain. So actually, if you run a Y number sum, you find that first quartile, median, and third quartile is all zero. But we have a whole bunch of zero. So it might be a better way is just exclude zero the analysis and look at that, because you have to think about what happened to this zero. The actual, the zero here probably include actual zero, no investment at all. And it could be there's zero capital gain, right? There are two parts for explanation about having zero gain. So, you run this capital gain, the frequency capital gain, and then you can get a list of unique values of capital gain. There are too many here, so I didn't put it out. Okay? Here we just do the plot. Okay? This capital gain very straight. Supposed to be plot the capital gain. Because we have so many zeros here. So this may not be the best result, so you might want to exclude zero for analysis and see what happens. So zero capital gain is dominating, maybe a whole bunch of majority are zero. Okay? Even after third quartile is zero, right? So maybe you want to exclude that. Okay. In addition to that, okay, so here, this is without zeros included. Okay? Zero is excluded in this part. Anyone spot this number? There's a number 99999. 99,999. Is this true?
We had 100,000.
Well, so maybe this is not a real number, so maybe just represent that over 10,000, or 100,000.
One person.
Okay. Because of that, right? No, there's one that is kind of disguised by this. So maximum the capital gain. Is it just one person? More than one? Huh? Yeah. So So here you just say this number, right?
So gain equals.
There's only one. Just how they merge together. No. Sorry. There's one number that's 9. Yeah, that's exactly that. I already have that frequency of a gain there. So actually, I'm going to do this.
Gain greater than equal to.
Get a frequency. Actually, it's this. Actually, 159. That number. It is very 99,999. I don't believe this is the actual number. This is probably the representations of, say, maybe 100,000 people. There are 159 such individual religious categories. So you can actually look at this from the original data set. You can actually count that. Can you look at this capital gain for this number? So, yeah, I already calculated the frequency. Yeah, original data. This many. 159 counts of this 99,000. This is probably more likely to be 100,000 or more. So that's why here, sometimes you look at, just take a look about the data set. This value probably questionable. I'm not sure with. So in the old day that when they do survey, some huge number also used to be to present missing value. So could this be missing value? Did he explain that there? Anyone look at it? He mentioned about missing value code for this one. I don't know if this is a missing value code or probably just some right sensor value. Representations of $100,000 or more. So really hard to know. Suppose we exclude that from just look at the remaining observations here. Let's start that again. So basically all you have to do is just frequency of the gains, plot against gain, and type it this sort of this high value, this sort of high value. And the subset is gain is positive, so we exclude 0. Okay. And also that the gain is not equal to this 99,000. Just to that subset. That's produced this graphic. So here view of other results. Well, the data is there, but they didn't explain about this number. Did it? Anyone see any document regarding this? Probably didn't explain, right? I kind of suspect this number is not real. So maybe either it's missing value code or it's really a sensor value, right? So we do not know about that. Why we need some other document. Remember, this is an estimated result from. I believe this is between sensors. Was it this 1994? I just say So maybe between 1990s and 2000, they had this, they will use the information estimated values for that. And usually they do some kind of estimation, look at the census result. Like here, the 2010 result, they probably also forecast like 5 years later, the result 5 years later, projected numbers for that. But maybe this is because of that. I'm not sure. Now we need to go back to check the original data, the report about the census result. What kind of code to use to code this calculation. If you look at the capital gain and the capital loss combined, of course this is my interpretation, this may not be true, but we need to go back and check this. This is what happens if you table this for those capital gain greater than 0, table with capital gain loss greater than 0. So here the row is capital gain. See what happens? Because this kind of tool you can usually store it. I don't have to. You know, this doesn't need to be the primary problem. You know, but we understand the data. So here, there are basically this many individuals having capital gain greater than 0, right? But it just comes with no capital loss, right? And then the capital loss, some of this, it's hard to explain. This may be maybe capital gain and capital loss is just two in one variable. So. Of course, when I do this, we should not do this without consulting the original documents about this. If this really makes sense, you can look at this. Capital gain minus capital loss and see what it's done.
So perhaps they should have had a column with no investment and another one with capital gain of 0.
Yeah, could be that. So you can see that the result, right?
Yeah.
Capital gain, then you have no capital loss at all, right?
Well, capital gain could be a negative value.
Yeah.
Capital gains could be negative.
So maybe this is two in one variables. Okay. I'm just saying maybe. Okay. So when you do this, okay, so every step you should keep the rationale about that and try to find out whether the result is good, right? We are not just producing off the whole bunch of output without knowing what's going on. Now, assuming this is okay, and then you say define net as a capital gain minus capital loss. That's one way to look at the result. And then just open that again. Just look at the frequency for the net result. Now this again, we exclude the 0 and exclude that number, space number again. And then you look at you can plot the frequency distribution of net by salary growth rate. Here, everything we have done above can be put into a function, and so you can just use this function to make a function for the result. I wrote this function myself, so I hope that this will be useful to you. So suppose I call this function capital F rate, okay, for frequency, even a numerical variable here, x, and then here g is a booking variable. They are supposed to be of same size, same length. And p is the number of levels of g. So g must be a vector, same length as x. And p will be the number of levels you have. And basically this function will just do the fit. Just do that. So I kind of redo that, this data frames of this capital gain minus capital loss. this data set. Well, sometimes writing function is not as difficult as we thought. You can write very simple functions. And then you can do a lot of work. And let's plot the frequency distribution for this. So here, this will be a comparison of, if you look at this net gain of this less than equal to 50K, so what is the equation about this result? We expect the result of this. For those that are winning this, say it is 50K, more than 50K, you can see the result of that first one. It's net gain. You can feel more concentrated. Usually it's smaller value, right? And it gets in less than 50K. So maybe this variable is somewhat related. Could be a predictor for our target variable. Of course, only if this makes sense, right? we have to check whether the way that we kind of find this new variable. I've done this before without actually creating new variables, so this is another way we get. So variables, education number is sort of 2 in 1. Exactly. This is actually what happened. If you actually run this result, you can see that. These are education number, and if you do this reordering the education, remember this is our vector column, right? Okay. Reorder these vectors according to education number. So here, the levels are sorted, reordered according to the frequency. Not frequency, according to the education number. So according to this frequency. In that order. You can see that. They are actually aligned. So basically, these two columns are actually, they carry the same information. Except one is just for the order. Sometimes you also need to look at this. If you run a correlation between these two columns by converting the vector columns into numeric variable, find the correlation if you want, right? You can actually do that. So here, you can actually do this. So here we have correlation of this education. So now, this is already numeric, so we don't need to make any change to it. And then, that's why sometimes the typing commands is more helpful. Just using like point click is rather. Some of this cannot be offered directly from like software like that. And making this numeric, this education this is the right order. Oh, okay. I got it. Because the way we set up education is not, we use alphabetical order. That's why that's this one. Sorry. No wonder we didn't get exactly the correlation one. Okay? Sorry about that. Actually, earlier I already showed that at the very beginning of this solution, I already showed that they are actually fine. So I shouldn't have used that. Okay, so where are we at? And you can reorder the levels of education according to the increasing order proportion of that. Actually, this part, actually, I don't have to repeat very similar to what we did EDU2. So we set up this levels education to be in line with that. So actually this is identical to that, to what we did before. But this is another way to like reorder this. And this mosaic clusters will be identical to what we have seen before. Yeah, this is another way of regrouping, not exactly identical to what we had before. Including some college degree, not some college courses, okay, some college experience anyway. And then here there are two associate, right, degrees, right, professional and academic. Right? And then here there's bachelor's and master's and PhD or professional groups. This is another regrouping. Okay? If this makes sense, then you can look at the result. Okay? And then you can make it as an ordinal variable. And then you produce a mosaic plot. Okay? So see, this is the result that we have. I still need to turn it sideways anyway. Okay? We can still see this increasing trend on that. Okay? And the moment I put this on, and then later on I screw this. Okay? And this is final weight. This is some kind of weights that they use to to carry this the census result. The weight is proportional to population sizes. So actually carry no information about this data. So I guess I'm going to leave this up for now, and then I'm going to upload this example. I need to modify this. Okay, some of this it's not ready, okay, to be loaded. So okay, we should go back to our discussion. Where are we at last time? I think we are. Certain points here. Actually, the basic idea of this tree model is that usually the parents are impure comparing to the child nodes, right? And you try to make child nodes as pure as possible. So reduce impurity. So actually that's the idea. Here, purity or impurity really referring to say this number of misclassified identities or smaller proportion of misclassified identities. Okay. So the child nodes hopefully would be represented by say majorities of a particular class. And I think we talked about this. And last time I talked about estimating true classification rate. Okay. One way is using cross validation error. Okay. The V4 cross validation. And this the list here does not exhaust the possibilities. Okay. There are some you can also use a bootstrap resampling, okay, which is actually used in the packages characters here IP. You use a bootstrap resampling. And some suggest the cross validation. Say V4. So for example, if you do 10-fold cross validation, some suggest you could also repeat this for say a small number of times, not just do it once. Okay. So you first split the sample into like say this is 10-fold. Split your trained data set into like 10 sets of approximately equal size subset. Okay. And then you do training on 9 of them combined, and then use the 10th one to test, to estimate the error, and combine the result. But here, some suggest this not only done once, but you repeat a few times, like 3 times, 4 times.
instead, and then try to make this the errors estimate more reasonable. Okay? So anyway, here, but this is like this is general result about estimating the true classification rate. Let's talk about something about the tree construction. Okay? First of all, how to split. Remember, the criteria is trying to split a parent node into child nodes, okay, so that the child are purer than the parents. Not just pure, right? In hope that ideally each child node is pure. Okay? Means it contains only a majority will be from one class and the rest like very small number of individuals coming from the other class. Okay? So actually that's what we talk about purity, right? So the problem is how do we split? Okay? So how to choose threshold value to split? What kind of value? Remember we talked about at the very beginning we had this example tree model. Okay. So original we have 50 Setosa, 50 versicolor, and 50 what is the other one? Virginica, right? This node is not pure because we have mixture of the three groups. Okay, and split down to that. But here this is really pure, right? This node contains only individual from just one class. Okay? Of course, this is also, of course, purer than that, but not compared to that. Okay? This completely like 49 individuals come from one class, but only 5 from the other class. Okay? Okay? That's, of course, much better than the parents node, right? Well, not at this one. Actually, we didn't see the split here. We should see the split here. How many do we have in this? So actually, after this split, we should have 50. Still have 50 versicolor. We have 0 from Setosa, 50 from versicolor, and 50 from Virginica. So at least purer than the previous one, right? Here we have 1/3, 1/3, 1/3 in each class. Here we have this represented in this node, in this child nodes we have what? We have 0% for first group, right? And 50% for second group, 50%. So at least that node is purer than the parents. Okay? And in further divides, so these two much better. Now this value is called the threshold value. So how do we determine that? Okay. So basically this is a subject that we talk about here. Okay. So how this threshold value is chosen to split, okay? And when to start splitting, because you can grow a tree indefinitely, and the tree model becomes more complicated, right? With small nodes, the result is more complicated. Okay? And which class should a terminal node be assigned to? Of course, we already talked about that. We use a majority vote, right? Okay. So here, this is example. The idea is to make the descendant nodes or child nodes purer than the parent node based on an impurity measure. Okay. So here, this is a 3-class example like this. Okay. The marginal distribution of 3 class in this node as this, right? Okay. Well, probably our example of this, our iris data could be a good example. If I make the middle, the class in the middle as Setosa, the other two as versicolor and Virginica, basically that's sort of schematic class of that, the first split, right? Okay. So here we have 1/3, 1/3, 1/3 distributions of the 3 classes to begin with, right? Okay. So 1/3 Setosa and 1/3 each for versicolor and Virginica, and with this split down to here, this class is purely just Setosa, right? Okay, it's probably the 1, right? Okay, and the other nodes will be half of the versicolor and half of Virginica. But this, the child nodes are purer than the parents. Okay? Here, where you have like a mixture of 3, here we don't have a mixture of 2, right? There are only 2 classes left. And impurity functions defined on the probabilities of, or the class probabilities, and these are called class probabilities. Okay? so that achieves the maximum only at the uniform distribution. Okay. The maximum impurity is at this equal distribution. Right? This is maximum impurity. Okay. Achieves minimum only at the corner points other than the origin, like here. This is so here, like this case, this is purity from class 1, and this is from class 2, and so on. Ideally, right? You have the result like that. Okay? And it is a symmetric function, okay, of these class probabilities. Basically, there are 3 types of impurity functions. The first one actually we used before is called misclassification error. Actually, it's done by this one minus the maximum of P1 to Pk. Okay? And Gini index is given by this. If you take a look about this, what does this tell you? I don't know. For Bernoulli trial, this is a variance, right? Isn't it? So here, if you have multinomial distribution, no, not just by multinomial. If you have x1, xk for multinomial with like n observations or n trials, okay, and then probability of success p1. So basically, these are our class probability, right? Okay. And for any particular observation or particular trial, the probability of observing class I is given by this class probability. Okay. So you know that, right? So here probability is that x just a particular observation. That is this. Okay, suppose I use that as a vector, much easier, right? So here, just take one example here. So here, this is class probability, right? For any instance, okay. You I should say this is trial number 1. Otherwise, this is okay. Trial number 1 result in class 1 with probability of P1. Okay. And actually, you can actually see that the variance from this, okay, from this x I would be pi 1 minus pi, right? That's the variance of that. Okay. So basically, Gini index is the total variances. Actually, in multivariate sense, this is what is called total variation. Actually, by summing up all the variances, okay, without considering the off-diagonal elements. Mean off-diagonal elements are the covariances. So we're not looking at the covariance structure. That's a Gini index, okay. And the third one is basically based on the information theory. This is something to do with cross entropy. Okay. Okay. You look at the statistic 562. You think about this feature information. It has some format like this. Okay. Feature information. Okay. It has some form like this, but this is based on information theory. Okay. Actually, I have plotted this impurity function when you have 2 classes on it. Okay. So here, suppose the P is P1 basis. This is class probability for class number 1. Class number 2 will be 1 minus P, right? So basically, this is the result. Misclassified error basically is this, okay, this triangular function. Okay. You can see all this rich maxima, okay, and the most impure result, isn't it? What is that? 1/2, right? Okay. The maximum is reached at 0.5, where class probabilities are 1/2 and 1/2 most pure. So actually, that's sort of the first condition that we mentioned satisfied, right? Achieve maximum only at the uniform distribution, right? 1/2, 1/2. Okay. And achieve minimum only at the corner points, actually also seen here. Okay. This is what at this point means that the class probability for class number 1 is 0. that for class number 2, that's 1, right? Okay. P1 is 0 and P2 will be 1. Okay. So here this is corner point, both ends of corner points. Okay. So all these are satisfied. Okay. In fact, when I did this, I do like a rescaling of that, because the function you see there is not really scaled down to that. Okay. This maximum and minimum. So do some rescaling design. Okay. So entropy was rescaled, and Gini index, you can see that. Okay. They are slightly different. Okay. Gini index sort of come in between these two results. And when you have this the other one. And impurity measure for node T, at any particular node, okay. Impurity function is evaluated at the class probability at that node, okay. Isn't it? And this phi function is our impurity function we mentioned there, okay. So using any impurity function and evaluate at the class probability at that particular node, at node T, what is the chance of observing class 1? So what is the chance of observing class 2 and so on? So it's basically for any particular node, the impurity is measured by this impurity function. Okay? If a split S of node T sends a proportion PL of cases, okay, in node T to its left child, so use TL. Well, actually, it's probably so we have to use this notation to try to illustrate this result. Okay? TL for the left child node and TR for right child node. For that, okay? And the proportion of PR to each right child nodes, of course, you understand PL plus PR is 1, right? So, okay. Then we have this result. The goodness of split S is defined as this. Okay? This is the impurity, okay, of the parent node. Okay? And so here this the goodness of split base is measured by subtracting the weighted. Remember, PL is a probability, right? That will split into that, right? Okay. And ITL, this is impurity of left child, okay, and ITI is impurity of right child. Okay. Because you have the chance of going to the left node with this probability PL. So in a sense, these two combined are the the sort of weighted average impurity, right? So the weight is given by the probability. So actually, you can see that. Okay. So IT minus, maybe I should write this. Okay. So here this is PL. Okay. ITL. Okay. Plus P IT. So ITL is impurity for left child, and ITI is impurity for right child. Okay. And well, to go to the left child, okay, the probability of going to the left child is probably PL, right? So actually, in a sense, this is a sort of weighted average of the impurity of the two channels. Okay. So the goodness of split is measured by this. Ideally, what do we want in this case? We try to maximize this, right? Isn't it? We try to find a split so that the goodness of split, okay, could be, well, ideally, we want that to be maximized, meaning that, okay, this the impurities the impurity could be, so here this would be pure and this less pure, right? Okay, so ideally we want this result to be as small as possible, okay? Because IT measure impurity. The best result is that both child nodes are pure, right? So in that case, both means 0, right? So best result, okay? So basically this measure the goodness of the split. So we try to maximize this. Okay? So the idea of finding two child nodes is try to maximize this. So that's why this is so-called, this is measure the goodness of split. Now, if it turns out that the weighted average is near the impurity of the parent node, you didn't get much, right? Isn't it? what happened? Of course, probably we won't find that kind of split. What happened if this the impurities of both child nodes are identical to the parent node? This result could be just 0, right? So that's what we try to avoid, right? Try not to have 0 goodness for this major, okay? But we try to maximize this result. Okay. So basically here we kind of try to maximize the overall reductions in the impurity, right? Actually, this is the idea for this formula, isn't it? Okay. We don't have to understand how this was derived, but understand what's meaning of this. Okay. Is it number 3? Okay. This one, right? So here, let's say T is the terminal. It's a terminal node. Okay. So we just look at the impurity at the terminal node, and again, this is the weighted impurities of the terminal nodes, right? Isn't it? Okay. So when you want to compare the impurity of one tree versus the other, we actually use this measure, okay? The impurity of the entire tree compared to the other tree model. Okay? And this is probability of coming down to this terminal node. Okay? Of course, in our case, probably the probability we're coming down to this with this spread, you can use cross probability to estimate, right? So basically, this spread is like the chance of spread down to this is 1/3, right? Isn't it? The chance going down to this 1/3, estimate by 1/3. Chance going down to this node is 2/3, right? And then go further. Okay. So the chance of the terminal node is the probability going down to this, and then times the probability going down to this, right? That would be the probability for that. So, but anyway, you take all the terminal nodes and calculate the impurity, and here the weighted the average, so the weighted average impurities of all the terminal nodes will define the impurities of the entire tree. Okay, that's what we have here. So that's how we have this impurity measure for tree with a set of terminal nodes T. And the best split is selected to split a node to minimize the overall tree impurity. So actually, that's the basic idea about that. Okay? We don't have to know the detail how the algorithm was implemented, but this you understand the split there. Okay? For the tree model, okay. And for the tree model, each split depends on only just a single input variable. Okay? And here, this is the concept of split. Okay? If you have quantitative variables or ordinal variable, okay, xi, S includes all splits of all the form xi less than equal to c. So basically, naming that if you have a numerical variable to start with, and with your data, first you find set of distinct values in your data. Maybe because of running of errors, some of the data values are identical, right? But let's say for your data set, okay? Let me erase that. So for any like a continuous measure, you have this original data values x1 up to xn, okay? And of this n observation, n values actually they are only says just say m distinct values. Okay? Suppose let me use that y1. Okay. Of any of this y1 to yn is they all comes from this set, but they are all distinct. Okay? So maybe you can just let me just write this out. That'll be easier. Okay. So this could be some y1 less than y2. Just find a set of values that are distinct out of this your numeric variable. And for ordinal data, of course, according to the coding and ordinal data, we already know that the levels 1 would be less than level 2, less than level 3. So actually that fits in also to the ordinal data, assuming that in ordinal data you have m levels. Okay? So either way, either you have quantitative variables or order categorical variables or basically this ordinal data, right? And so it will include all the splits of the form basically they are possible of this many split. You can split right here. Okay? So leaving one y values on the left and the remaining n minus 1 values on the right. Right? Okay. This is one split. Another split could occur here. So in this case, you can have total. Okay. You have this n minus ways of splitting this result. So basically, this will define the split for any particular quantitative variables or ordinal variables. Of course, for quantitative variables, you need to find a set of distinct values first, and the treatment to this, will be similar to like order category. And C is restricted to the midpoints between consecutive order data values in the learning set. So the split basically take the midpoint, so y1 plus y2 over 2, right? And then y2 plus y3 over 2. Anyway, the split in the middle. Now, how about for the categorical data? You cannot say use the average, right? Simply just set aside, how many observations would be belonging to the first category, how many belongs to the rest of the categories, and so on. So that's kind of split that we talked about. Okay. So with quantitative variables or ordinal data variables, we could have n minus ways of splitting the data, right? Okay. Next one. How about nominal? Because there is no particular order, so it's more complicated splitting, right? Okay. You could split the data in like suppose you have here like this one you have having error levels. Okay? You could split the data into one group having just one of these error levels, and remaining error ones, error minus 1, right? And a number of ways of choosing that as well. Okay? So you could have this many ways of choosing the splits, right? Okay. So this split into groups of 1 and error minus 1, right? The number of ways to split into group of 2s and error minus 2. Okay. So you have this many ways. Actually, it will be that number is 2 to error minus 1 minus 1. Okay. So you have for nominal variables, you are having this many possible splits. Anyway, this is. So you really need some good algorithm to handle this nominal data, especially when you have huge number of levels in nominal data. That's very hard to do. Okay. Some kind of algorithm is required to do that split. Okay. So that means you look at this. So each split depends on only a single input variable, and then let's say you have 3 variables to start with. Okay. So you have to first look at individual variable, and you have suppose you have categorical or ordinal data or numerical data like this, and each that categorical ordinal data or quantitative data will have n minus way of splittings, right? Of course, among them, one will produce, or at least probably there's some ties. Okay, one will produce the best split, right? And look at the goodness of split. Remember we mentioned about that earlier. Look at this goodness of split, and look at that. Okay, and then look at how good that split is. But you do this for overall. Let's say we have only 3 variables to start with. Okay? So we have to deal with the individual variable. And among these many ways that can find one that provide the best split. And sometimes ties could occur. Because you can either choose one randomly or just pick the first one, the convenient one. This probably occurs here in this tree model here. If you model this tree model, to put the payload length first. Okay, payload length occurs first. You can also model the other one payload width first. Of course, the split probably is not there. Payload width at the first split could come up. Okay? They are equal probable. Okay? Okay, you can have the data like this. Okay. So number of splits really depends on the variables. Okay. And each node search over all input variables beginning with x1, continue up to xr. Okay. All the features, and for each variable find the best split. And among all the variables, compare these best splits and select the optimum one to split. So it's actually that's the idea we just talked about. Okay. And that will commence the sort of give you the first bit you see there. Okay. Like our iris data. Okay. And class assignment, well, of course, in case of categorical response, class assignment is based on by majority vote. That's all. We already seen that, right? Okay. The class assigned to node T is okay. The class is the one that maximizes okay, the class probabilities given that node here. Okay. Remember that's a posterior probability, right? That's a probability that you see there. Okay. They maximize that. Okay. And random assignment is used when two or more classes achieve the maximum. You can use that. Okay. Or maybe pick the convenient one. Maybe. I think it should allow some randomness would be the best. Okay. If you have some ties that occur. Oh, by the way, I forgot to mention. Some of you asked about incorporate the course structure in your analysis. Yeah. I forgot to mention that. Actually, the course prior to adjusted prior is done by this. Okay. The course of misclassification, or the prior is proportional to this, or this additional adjustment, right? Adjustment is in this proportion. Here you have C1 to P2. Okay. Here P2 is prior for second class, and then here this is given that the true identity is second class number 2, but you misclassify as first class. So here this is misclassified cost, right? Okay. Given that you have the actual identity of class 2, but you misidentify as coming from 1. Okay. It's proportional. The adjustments are proportional to this. Okay. So here this is C21. Okay. P1. This is for class 2. You need to make this adjustment. Okay. Now, without the course structure, mean that these two misclassified codes are identical. Basically, the proportion will be just prior second class versus first class, and usually that is set by the sample size, right? Or unless you have some priori information. If that is the case, then you do this adjustment. But how can you adjust this to like proportion? Because most software only show that you specify the priors, not the cost structure. Okay? This is really simple to do here. Simply just do this weighted average of that. Okay? So these two proportions will be similar to this. This is 1, 2, right? Okay. So if you have this course structure of say C12 and C21, okay, then you adjust your prior by this. Remember, in these two, they are both positive. These two add up to 1. Okay. So basically, that's an adjustment for that. Okay. I forgot to mention that. This is in your case study, in the credit data. They mentioned about this course structure. I forgot to mention that from the beginning. Things at the end, they talk about the course structure here. So here the data set requires use of course matrix, where the rows represent the actual classification and the columns the predicted classification. So for example, here C21 is this, fine, right? Isn't it? Is is C21, isn't it? The actual identity from class 2, that the cause of misclassify is 5, as against the actual identity is 1 that you misclassify as 2. That's 1. So actually, you're doing this adjustment. C21 is 5, C given 2 and 1. Okay? The true identity is 2, but you misclassify as 1. The close is 5. That's up. That's why you have. So you should have this 5 times P2 over this 5P2 plus what's the about the other close?
1.
The other is 1, right? So that's 1. Or just P1, right? Okay. Just write 5P2 here. So is this in this proportion? And then here you have like P1 over 5P2 plus P1. So actually you readjust your prior according to this. Okay? Make sense or not? Okay? I guess for the class, the priors is, I think that in the data is about 70 to 30 split in these two classes, right? 70 is for class 2 or class 1. Okay. Class 70%
Is good.
good, so that's class 2, right? Okay, but anyway, either way, so it should be able to adjust this file. All these classification function LDA, QDA, they have the additional arguments and priors. That's the place you can specify these priors.
What function is?
But LDA or QDA have this additional argument that's called priors. Okay. So I didn't mention that earlier, so sorry about that. For example, linear discriminant analysis, there's this argument called prior. This is the place you can specify prior. Okay. Can you finish your project by Thursday? Yes or no? I think students always say no. I want this course, like everyone take it easy. You know, this is. I hope that this is fun class to learn data mining and also learn R altogether. So, how about is it enough time that postpone due date to next Tuesday or not?
It's already.
It's due next Tuesday.
Oh, it's due next Tuesday.
Yeah.
How about next Thursday?